paleontologists, 50 million years from now, were to prospect for fossils in the rocks of the Anthropocene, what would they find of us? What will our fossil record look like? In this video, we consider how easy it will be to find us in the sediments of our times, and then the nature of our body fossil and trace fossil record. We can start by considering just how visible our record will be in the vastness of geologic time. Modern humans have been on Earth for about 70,000 years, with archaic humans around for the past, say, 200,000 years. Settled society started about 8,000 years ago, and we've made extensive use of metals for about the same period of time. Industrial society is much more recent, say only 150 years old. What do these time frames imply about the likely sedimentary thickness of the Anthropocene, and therefore how easy it will be to find fossils of us? In the deep sea, typical sedimentation rates are 1 to 2 centimeters per thousand years. Modern society therefore represents about a quarter centimeter of sediment or less. Our record of settled society represents maybe 6 to 16 centimeters of sediment. In other words, a paleontologist would need to be really looking for us to find us, and the effort would have to be rather substantial. If we make these same calculations on land, the record is a bit more permissive of actually finding our remains. Typical terrestrial sedimentation rates are upwards of 50 centimeters per thousand years in floodplain soils. Therefore, modern society represents, say, 10 to 15 centimeters of sediment, and settled society spans maybe 3 to 4 meters of record, a sequence whose thickness approximately matches my height. Of course, humans tend to increase sedimentation rates, at least locally, so a future geologist could get lucky and find a delta or a lake where there's really a good record of us. The point is that a future observer would probably have to be looking for us to find us. A quarter centimeter of open ocean sediment is not much, particularly after bioturbation has occurred and mixed everything. The situation is better on land, where there might be a few meters of record of our time, but a future observer will still need to be lucky to find us, given geologic records with kilometers of sediment in them. Another problem is that human population was low enough for most of our history that human fossils are very rare before the Holocene, that is, the last 10,000 years. Hence, our pre-modern body fossil record is probably invisible to an observer 50 million years into the future, since it's already pretty sketchy for us. The situation is a little bit better for modern society, but only a bit. Today we are helpfully populous, meaning that there are lots of opportunities for somebody to be preserved. We also lend assistance to natural sedimentation by planting our dead in graveyards, avoiding at least some of the active zone processes. But unfortunately, we also cremate a lot of our remains. Worse, we tend to live in upland settings where erosion is fierce. We are probably always going to be pretty rare as fossils. Even if our fossils are unlikely to be particularly abundant, we have had a major impact on Earth that will surely be visible, and some of those impacts started well before the beginnings of modern society. For instance, hunter-gatherers certainly contributed to the Megafaunal Extinction at the end of the Pleistocene, when saber-toothed horses, mammoths, camels, and short-faced bears all became extinct in North America. That extinction eliminated whole groups of animals in Australia and Europe, too. The disappearance of these animals will be visible long into the future. To be sure, we will still argue, like we do now, about when some of the megafauna died out, and that problem of determining when the extinction occurred will be vastly bigger in the future. Still, the extinction is a hard fact that says something unusual occurred that caused a lot of big animals from many different clades to vanish. Of course, we could do stuff that would make the megafaunal extinction even more visible. We have not yet driven many major clades extinct. Even relatives of the megafauna, like modern lions and elephants, are still around. However, we are pushing many major clades, like big cats, great apes, tunas, rhinos, and so forth, towards extinction, and their loss will be recognized in the fossil record as range termination of major vertebrate groups, even if the exact timing is very uncertain in the future. Given sampling problems, it's unlikely that exact causes can be given for the extinctions from the perspective of a future paleontologist. But those paleontologists of the future will know that there was an extinction, and they will go hunting for answers. On the other hand, if we start bumping off major groups of rodents, say, which have a very dense fossil record compared to the megafauna, then a future paleontologist just might be able to pin the blame directly on us. There is also the matter of our stuff, namely what our trace fossil record might look like. We make some durable materials, which in principle could survive far into the future. Glass and china, for example, although they devitrify over 10 or 20 million years, are still up to that point essentially inert rocks. Bricks can also last for the ages in dry environments, but they will swell over time if there is moisture, because the water was baked out of them during manufacture and then is reabsorbed over several centuries. Concrete might survive, since it's essentially a sandy limestone, but it will decalcify in acidic soils. Since we tend to produce a lot of organic matter that makes acids, ranging from organic waste to fertilizer for landscape plants, we predispose the environment to destroy our concrete structures. Plastics, of course, are famously resistant, but after 50 million years in deep burial would convert back into petroleum or tar. Plastics also fragment when exposed to the sun, so an outcrop of the Anthropocene is more likely to contain tiny pieces of plastic than whole single-use water bottles. Of course, some architectural stone, carved granite for example, is highly stable if protected from water and surface erosion processes. If you want a nearly indestructible epitaph, then granite is for you. Other types of natural stone, like slate and limestone, are highly unstable when exposed to weathering or acid rain. However, even these are quite stable if buried and protected from active zone processes. Even if fossils of us and our stuff may be somewhat paltry in the future, some of our trace fossils will be really hard to miss. For example, we are masters at soil erosion thanks to agriculture, industrial mining, and refashioning landscapes for roads and cities. These activities increase sedimentation in floodplains, ponds, and deltas. We also dig mine shafts and wells, and these holes in bedrock may be preserved for many millions of years. Further, we excavate building foundation, underground pipelines, and commuter tunnels that have pretty good prospects for sticking around long into the future. Further, if you want to personally be preserved for the ages, one solution is to be dumped by a criminal gang into the cement in the foundation of an underground parking garage. Your remains are already encapsulated in rock and are instantly in the historic layer. Another booming signal of our society is that we have dug up most of the rich native ores and are often now mining deposits with metal abundances in the range of grams per ton. Our remobilization of metals should turn up as a spike in metal abundance in sediments dating from our time. Many of these metals will be visible in the record in the parts per million range, but will still be readily detectable with mass spectrometers. For example, a record of lead concentrations in Greenland ice cores holds a history of the wealth and changing fortune of the Romans as lead and silver flowed into and out of the Roman Empire. These same ice cores also hold a copper spike associated with the first open-air smelting of copper in the Middle East and Europe during the Chalcolithic, or Copper Age, 7,000 to 8,000 years ago. Part of our trace fossil record is in our massive carbon isotope signal from fossil fuel consumption. There is a developing negative carbon isotope excursion from burning carbon-12 rich fossil fuels. This is called the Seuss effect and is visible in everything from wood to corals as a gradual drift in carbon isotopes through time towards increasingly negative isotope ratios. If we continue to use fossil fuels over the next 200 to 300 years until fossil fuels become quite rare and expensive, the resulting carbon isotope excursion will be pretty big. This carbon isotope signal should persist in the environment for more than 200,000 years. Now, accompanying this carbon isotope excursion, we should see diverse evidence for global change from greenhouse gas injection into the atmosphere and the ocean. For example, the planet is already warming because of our activities, and that temperature signal will be detectable above background for more than 100,000 years. Another signal is ocean acidification, caused by dissolving fossil fuel CO2 into the surface ocean. That signal will last 7,000 to 10,000 years and will be seen as an ocean-wide interval in sediments in which carbonate is extensively dissolved in the deep sea. The interval of low carbonate abundance will be particularly visible in parts of the ocean that are rich in seafloor carbonate ooze, because with the ooze gone, clay and other insoluble minerals will be much more abundant. Finally, depending upon how bad acidification gets, we could see extinctions of major clades in the oceans, like the Permo-Triassic extinction event. My point here is that we can foresee what our archaeological record will look like through our understanding of fossilization, taphonomy, and paleontological models. Probably our most visible effects on Earth are our impact on extinctions and the geochemical fingerprint we're producing right now. Our geochemical footprints will send up a big flag to future paleontologists to puzzle about just what went on in the Anthropocene. As it happens, we do not have to guess at what that future holds, because we have an actual example of events in deep time that show us how the world has dealt with global change very much like what we are producing right now. That glimpse into our future from the deep time of Earth's past is what I will talk about next.